Welcome all to our Renishaw Equator Coffee Break. I am Dragos Leu with the sales team, and we here at CMM XYZ have started a new series of virtual events, Metrology Coffee Breaks, in which we would like to share with you the metrology news and information to present different technologies and the latest improvements. Today's event will focus on the shop floor flexible gauging solution, namely the Renishaw Equator. This unique measuring equipment can perform comparative measurements, but also verification to CAD nominals. My colleague Allan has prepared for this coffee break an example of application on the Equator 300. He will also talk about the larger Equator 500 and the extended versions of the Equators. He will discuss a simple study and analysis of results. Allan will now take it from here. Please enjoy the presentation and the coffee.
Thank you very much, Dragos, and thanks for joining us this morning. I've prepared a couple PowerPoint presentations, but I want to try and focus a little more on live content and some live feed from the Equator Organizer software while I'm running the show. I'm going to switch right over to a slideshow, getting over some of the basics of the Equator. So, first of all, what is the Equator? It's a comparative gauge, and it's useful in process control situations or, large volume production for final inspection and that sort of thing. It operates like a CMM. So what do I mean by that? It's got kind of a different structure. It's got this inverted pyramid structure here, but what it has the ability to do is to measure an XYZ, and it does have a touch probe on it. It is programmed with standard CMM type software, fully supported by the DEMIS programming language. So it's essentially a CMM. The main difference between the Equator and the CMM and what makes it a comparative gauge is the fact that it doesn't need calibrated on an annual basis. It doesn't need calibrated at all, to be honest with you. We do a process called mastering. To master the Equator, we need to have a part representative of your production. So it could be a production part, it could be something special that you've had made to represent, say, a perfect part for your production. But however that's done, we need to measure that first, and then the Equator is going to compare all of the subsequent parts to that first part. And we'll get a bit into that in a minute. The one thing that it does have as an advantage in terms of scanning performance and measuring performance is this parallel kinematic drive. So this weird kind of trapezoidal structure that it has. The way that the Equator operates, it's able to scan at an incredibly high rate of speed and still maintain accuracy because it doesn't have to worry about the inertial forces that CMMs typically do. The product line, as Dragos was mentioning, we have two main types of Equators. So the Equator 300 has been out not quite for 10 years, but it's been in the market for quite a while. And you'll notice on the far left-hand side, we've got the Equator 300, and then there's the Equator 300 extended axis. The 300 stands for a 300 millimeter diameter cylinder volume, which is 150 millimeters deep. The extended axis, the measuring volume is actually the same, but it's raised up to allow for larger fixturing or using longer styli extensions, etc. Recently, they've also launched the Equator 500 system. The Equator 500 system has a 500 millimeter volume, cylindrical volume, and it's 250 millimeters deep, and it also has an extended axis option. The one thing that you really want to keep in mind with this system is that it doesn't have a measuring uncertainty, it has a comparison uncertainty. As long as you follow a few guidelines from Renishaw, the comparison uncertainty will maintain its accuracy to plus or minus 2 microns. And I've got a little presentation later that I'm going to show you about that. Typical configuration of the Equator, just some of the highlights. It has an SP25M probe. The larger system, the Equator 500, can actually use an the SM25-3 modules for longer styli and larger lateral styli as well. A 6-port rack changer, stylus changer is also standard on the system. Uses these quick load plates, these fixture plates, so I can remove them and attach them as needed so I can run different jobs and change on the fly. It also has the options for like an operator button interface or a jog box, depending on how you want it to operate. I mentioned that we need to master the Equator, and I want to make sure we get the idea of how this mastering process works. First of all, the master part is required to set up the compare process, but the master part doesn't need to be a perfect part. It just needs to be a part from our production process that's similar to all the parts we're going to measure later. there's this kind of magic number, and it's not really a magic number, but plus or minus 1 millimeter. So the master part should measure within about a millimeter of what all the other parts are going to measure. And as I mentioned, it doesn't need to be a perfect part. How the comparison process actually works is we've got two methods. One is called CMM compare, one is called feature compare. Now, most of us are already measuring parts on a CMM, which is ideal for the Equator, because if you've got a program that supports exporting that file out into the DEMAS language, piece of DEMAS is one of those languages, we can use CMM compare, so we can export our program from our CMM and use that on Equator. We need to make a couple adjustments, but the bulk of the program would be there. In the CMM compare process, when we measure the part on the CMM, instead of only recording, say, the diameter of a feature, it records the deviation of every single hit that was taken on that part. With this ability, then, when we measure on the Equator, we're not comparing just the size of a feature, but down on a point level in CMM compare, we can compare pretty much every feature that we measured. The required method for the profile and form measurement. So if you've got surface profile callouts or line profile callouts, you're probably going to need to use CMM compare. Feature compare is a little different, a bit quicker and easier to set up, and it's the method I'm going to show you today. With feature compare, I only need to know what that feature measures. So when I load on my program and I run the Equator on the master part to set up the mastering process, I just type in the actual measured value or known value, and the software does a comparison for me. Very quickly taking a look at kind of a pared down version of how this process works. I've got a diameter here that we're measuring. We get a nominal hit value defined by whatever software it is that we use to program the Equator. Typically we use Modus on the Equator, but we can import from other languages, as I mentioned before. So we know what the nominal location of that hit is supposed to be. When we measure that on the CMM, it will know how far away that hit was from where it was supposed to have been and develop an offset value. This offset value is stored in what we call a cal file. So that file is run at the same time as when we're running the Equator to measure our parts, and that's how it figures out how much to offset each point by. Long story short, we calibrate the Equator to the part we're measuring at the time of measuring, and then there's some rules we have for how long that mastering process ought to have lasted. I'm going to switch over now to a live feed of the Equator software. Now, this is the Equator Organizer software for a demonstration part that we have set up here. One thing I do want to apologize for is we are using a webcam to record a live feed of a monitor. Unfortunately, it's very difficult to connect screen recording devices or attach the Equator's controller to a Microsoft Teams meeting. So this is the best I could do, but I think it looks pretty good. At least we can get the message across. So to show you guys how this works. So in this interface, across the top, I have two buttons, one on the left, one on the right. The button on the left is for mastering, the button on the right is for measuring. So I've got my program already set up, and I'm just going to master off of what I'm calling my master part, which is this connecting rod. This is a password protected option. We can turn off the password protection if you want, but that's to prevent operators from mastering, say, off of the incorrect part, and then it might skew some production values. As it's traveling around, it looks pretty cool when you're operating with the Equator because of the parallel kinematic design. You can see how incredibly fast it's going in there to measure that circle. I think that's actually scanning at 100 millimeters a second. And it's just going through and measuring exactly the way a CMM would. So the way it operates is identical to what you would see on a CMM. So once this finishes, I get an inspection report. This inspection report that you're seeing on screen here, I'm not going to pay too much attention to this. This is the uncompared values. Once I close that, we get the easy offset screen. So I've used feature compare here. So what I would be doing at this point, say I had measured the part on the CMM, then I would have a CMM report, and I would know that this circle, called circle top in my program, what it measured actually in the X, Y, and Z location, what its diameter was. If there was an orientation that I needed to adjust, I would adjust that. And that's available for every single feature that I've created a dimension for in this program. So as I scroll through, the first time through, if I wanted to, I could adjust these values. So this is how we would set up the compare process the first time we do it. There's no need to change anything because I've already set this up ahead of time. Let's see. Come back into the process monitor window. So what you see in the process monitor window now, I have a temperature range reading right now 0 degrees, and I've got a tolerance I've set up at plus or minus 2 degrees Celsius. If the temperature from the time I master the equator until the next time I master it, if it ever goes over that 2 degree range, it's going to prompt me to remaster because there's been enough of an environmental change to warrant doing so. So this is a really great way to compensate for thermal expansion. I've also got a remaster set up at 0 measurements, so I could tell the software, you know, after 30 pieces, after 100 pieces, whatever I want, you also need to remaster. Or the last step here is the a time duration. Some people will set this up for the production shift, so once at every hours they need to remaster. All the dimensions in the program show up in this view here. I can click on each one of them. It will show me the last measured value for whatever feature it was. And then I get a run chart down at the bottom here where I can see this little gold circle is my master point. After this point, anything I measure will be a run chart of the measurements compared to the first one. I keep talking about the comparison process. Very often in comparison process, what you would find is that the report would only show you, say, it measured plus 5 thou, minus 2 thou, whatever, but it wouldn't give you an actual measurement. Not so with the Equator because it is running a CMM software. You get an actual CMM report with the actual measured values. So while this part's running, I'm going to show you one other thing that I haven't even touched on yet, but it's probably the most powerful thing in the Equator. I'm going to click on this key icon and open up the admin mode. This is normally password protected, but I've disabled that for the purposes of the demonstration. And you'll notice for each of the dimensions that I've got inside this program, I also have a button for CNC setup. The Equator has the ability to connect live to your CNC turning or machining centers. When we do that, we can define for the CNC machine based on tool numbers that are mapped out to dimensions inside that we've measured in Equator. The software can actually start adjusting either the geometry or the wear offsets for things like the length of the tool. Sorry, I've got a message back here. All right, I'm going to work on this, but I'm going to switch over to a different part of the presentation. Just give me a second. The second part of the presentation, what I wanted to take a look at is there's another PowerPoint presentation for a case study that I was running. Because I wanted to get the idea across of how well this comparison process works. So I picked out something very simple that we've all used quite extensively in our careers, pin gauges. So I grabbed a 12.5 millimeter pin gauge to master or to set up the program. I'm just going to switch over to, actually I'll leave that alone for now. I'm going to randomly select 10 pins throughout a size range of plus or minus 1 millimeter for this test. When I got 3 operators to help me out, I took those 10 pins and each of us measured those pins 3 times each. And the Equator was measured only once at the beginning, or mastered only once at the beginning of the study. So long story short, I measured 90 different pins, or 10 different pins, for a total of 90 measurements. When I did all of this, and I recorded all of this information, so operator number 1, when I compared the pin to the micrometer size for it, I got 12.7 millimeters for this first pin that we measured. I called part number 1, and you can see the size deviations are incredibly low, less than a micron, less than half a micron in most cases. So then I thought I would do an analysis to take a quicker look at all of these results here. If you take a look at this, we've got down the left-hand side of the screen, we've got plus or minus 1 micron. for the tolerance that I've set up for this test. Now, I mentioned earlier, the uncertainty for comparison for the equator is meant to be plus minus 2 microns. I didn't get one value that was more than 0.7 microns away from its nominal size, or the actual size for the pin gauge. You can see the grouping of these measurements. I think the worst range was 0.7 microns, and the worst average value was about 0.6 microns away. It took me about an hour to measure all these parts, and I only mastered once at the beginning. So just wanted to kind of get the idea across over a very simple application, how accurate the system was. So the summary here is the Equator. It's a comparative gauge that works like a CMM for in-process measurement. It's flexible, it's accurate, and it's very fast and maintains those accuracies quite quickly. When I was measuring those pin gauges, we were scanning at 50 millimeters a second, and I was still holding roundness values of under 2 microns, and the measurements for the size were under 1 micron deviation. It's ideal for the shop floor environment because it is thermally insensitive and can directly control CNC machine tools for lights out production. So if you just give me a minute here, I'm going to try and reboot the Equator software and see if we can't fix this up. Okay, so I've got the machine rebooting. I'm just going to open up the live feed on a couple of things. Just give me a second. This should happen relatively quickly. I'm just going to change this plate out. So here's the little fixture that I put together for the Equator to measure this pin gauge. I've got a little, excuse me, chuck, just align it onto 3 points, attach my master pin, and there we go. I'm going to flip over to the Equator software again because I've got it back running live again. I'm going to switch over to the Ren compare process for my pin gauge measurements. Okay, so we're taking a look at a live screen of the Equator management software. I'm going to go into my pin gauge test program. When I open up that process management utility, it will give me the ability to set up a new master. I have my 12.5 millimeter pin gauge installed. I'm just going to run this. It's going to tell me it's not at its home position and ask me to send it there. Try that one more time. Go into the master process. So while it's measuring here, we're back online. I have a couple things that I wanted to go over with you. You can see the actual measured value of the pin gauge for the 12.5 millimeter pin. It's going to pop up here. And if I wanted to, I can click into this again and adjust that size if I need to, if there was an offset. There isn't in this case, so I'm going to leave that, exit out of that window. Click OK, and we'll just run this pin gauge. You'll notice it's off by about 20 microns, so this is kind of the Equator's inherent accuracy is about, in this case, we're within a thou, within 25 microns. And the roundness there, it's measured at 7.5 microns. Now that it's mastered off of that pin, it's able to perform that comparison process for its own actual measurements, and we get results of 12.5 millimeters, no deviation whatsoever, and still slight roundness deviation, but that's okay. So I'm going to switch over to a different pin value. Just randomly selecting these. I'm not sure what pin I have here. Run this again. This measures 12.6006 millimeters, and it is round within 2 microns. And I'll do one more, but I think you guys are getting the idea. Once we've got the equator mastered, and I know this is a very simple test, but at least I can run the program a few times for you and really demonstrate what's able to do in that comparison process. And this pin happens to measure 13.0997. I think the nominal is 13.1. We're going to switch back over to the Equator Summary. I wanted to go back and take just a quick look at the results I got previously, so I want to do this after the fact. But you can see all of these results are incredibly close to the nominal value, and not only are they close to the nominal value, they repeat to any one pin over the operators as well, and there was really no interaction that I could see between operators. I've already gone through the summary here, so thank you very much. Sorry for the little glitch there. Doing things live sometimes can be a challenge. Dragos, over to you, bud.
Thank you, Allan. Thank you, everybody. Shortly, you will receive a Q&A email from us. We will very much appreciate your feedback, including suggestions for future subjects to be discussed in our Metrology coffee breaks. We will be glad to provide specific information to your questions. Thank you very much for joining today, and we look forward to seeing you at our next Metrology coffee break. Have a good day.